All right, let's talk about what happens when we have lines and planes that don't intersect and how we find the distance between them. So we're going to go back to 12,561, which is the distance, or it was a previous problem up here somewhere. We're going to take a look at these two lines now, L2 and L3. And in this case, we're going to have parallel lines, okay? And so how do we know that we're going to have parallel lines? Well, if we write these lines out, L2 is actually, 1, 1, negative 3 plus t times 4, 2, 4. And then L3 is going to be, or s times 4, 2, 4. And then L3 is going to be 3, 2, negative 2 plus r times 2, 1, 2. And we see that this vector, the vector component of L2 and then the vector part of L3, they're just scalar multiples of each other, right? And so because of this, essentially what's going on is that L2, right, when s increases 1, when s goes up by 1, it goes that long, but when r goes up by 1, it goes half as long, right? And so that's what that is. So these are parallel lines, and so okay, and another reason why they're parallel, and you might want to check this, is that you want to make sure that these lines don't intersect, right? So you want to make sure that, let's say, 1, 1, negative 3 isn't, that L3 doesn't go through the point 1, 1, negative 3, right? So if we let s equal 0, then we get 1, 1, negative 3, and then we have to make sure that 1, 1, negative 3 can't be hit by this line, and it can't be, and how do you figure that out? Well, right, you got 3, 2, negative 2 plus r times 2, 1, 2 is equal to 1, 1, negative 3, right? And then you got r times 2, 1, 2 is equal to, this becomes, you subtract the points from each other, you get negative 2, 1, negative 5, and that's not a scalar multiple of 2, 1, 2, right? There's no r that can make this true. So in this case, then, they're parallel, okay. And so how do we find the distance from two parallel lines? Well, we want to turn this question, right? So again, we have two parallel lines here, and one way we can deal with this is that I can find a point on this line, and then what I can do then is then I can use the distance formula between a line and a point and a line, right? So I can just take a point here, and then I can just find this distance here, right? And remember how we used what the formula for our distance between point and line is, right? It's the magnitude of PQ cross V over the magnitude of V, right? And this was distance. Okay? And so in our case then, P is going to be, let's say, on this line, Q is going to be a point on this line, and then V then is going to be a vector, right, on that line right there. So then we say, okay, PQ, right, cross V, and then we find the magnitude of that, and then we divide it by V. So essentially, you want to ignore that parallel line existed, and then we just find the distance between that point and the other parallel line. Make sense? So, okay, so how do we do this? Well, okay, so let's say, in this case, we're going to let L3 be the line. And so our vector component then is going to be 2, 1, 2. Okay? And then we need a point on L3, which is going to be Q, and we can just take this point right here, 3, 2, 2, 3, 2, negative 2, right? Because it's when r is equal to 0. So 3, 2, negative 2. And then we can take a point on the other line, right? The point on the other line, L2, is going to be our point P, which we kind of treat as the point in space again, right? So imagine if this were L2 and this bottom line were L3, we kind of just pick a point on L2, and then we kind of just forget that that line is there, and then we find the distance from that point to the line, right? And since they're parallel, it doesn't matter which point we pick, because if I pick the point here, this distance is going to be the same as this distance back over there, all right? So we're going to pick P then as a point on L2, and we're going to pick 1, 1, negative 3. Why not? It's already given to us from the line equation, right? Okay, so now what is PQ? And PQ is going to be equal to 2, 1, 1. Okay? And I realized that whatever calculation I did up here was probably not right, but it's okay. So we get 2, 1, 1, and then V, right, and then PQ cross V is going to be IJK 2, 1, 1, and V is 2, 1, 2. Interesting. All right, and so that's going to be 1, comma, negative 2, comma 0. Okay, and so that's going to be the PQ cross V, and so the magnitude of PQ cross V is going to be the square root of 1 plus 4, which is root 5. And then we need to have root 5, right? And then we need to find the magnitude of V, which is the magnitude of 2, 1, 2. So that's 2 squared, or 4 plus 4 plus 1, which is equal to 3. And so the distance then between the two lines is root 5 over 3. Okay? So that's how we do the distance between two parallel lines. You pick a point on one of them, pick a point on another one, and then you use the vector on the other one as V, and then you calculate the cross product. So one good exercise to do then is pick a point on here on L3, and then use this vector 4, 2, 4 instead, and pick a point on L3, pick a point on L2, and then use this vector 4, 2, 4 instead of 2, 1, 2, and see if you get the same answer. And you should, right? Because parallel lines, it shouldn't matter which point I treated as the point in space, and which line I treated as the line that we're trying to find the distance to. Okay? Next part, this is going to be a long video, so hang in there, is the distance between, let's do, I know it says skew lines, but we're going to do parallel planes. Okay, and it's the same idea, right? The distance between parallel planes and distance between parallel lines is that you have two planes in space, and it doesn't matter which point I pick in like one of the planes, because it's going to be the same distance no matter where I am on the plane to the other plane, right? So we kind of just treat it as a point in space and the distance from that point to one of the planes, okay? And so then let's consider this example, and I have an example here. And so let's say we have a plane pi 1, which is equal to x plus 2y minus z is equal to negative 1, and then pi 2 is 3x plus 6y minus 3z is equal to 4, right? And so we need to make sure that they're not equal. Okay, well, they're parallel because they're just scalar multiples of each other. And, it's tempting to just divide this guy by 3 and then say this, then the right-hand side's 4/3, and then since this is negative 1, and so the distance is going to be 7/3, it's really tempting to do that, right? Because if you divide it by 3, now I got x plus 2, y minus z is equal to 4/3, and then it's just really tempting to compare these guys. That's not how you do it, though. That's wrong. So don't do that. Don't just do that. So how do you actually do it? Well, we do it the method I sketched out before we gave this example. So on one of the planes, then I need to find a point. Okay, and so let's say on pi 1, a point, right, is 0, 0, 1. Okay, and then what do we need on pi? What do you need for pi 2? Well, remember the distance formula for a point to a plane is pq dot n over the magnitude of n, right? Or this is the absolute value up here, and then this is the magnitude in the bottom. Okay, so n is the normal vector for a plane, and p is a point in space, and q is a point in the plane. So let's say let's say this is our point in space. Let's say 0, 1, 1 is our point in space. So now, P is equal to 0, 0, 1. And so now we need to find Q, which is a point in pi 2. Okay, and so what's a point in pi 2 that we can use? Does it matter? Let's see. What's a point in pi 2 we can use? 1. This one's a bit hard to eyeball. Yeah, let's just do something like, oh boy, I didn't expect this to be this difficult. Okay, let's just do 0, 2/3, 0. Okay, so that's a point in Q. This is in P2, in pi 2, and this is in pi 1. All right, and since Q has to be inside the plane, then our normal vector is going to be the 1 for pi 2, and it's going to be 3, 6, -3. All right, so what is PQ then? PQ is equal to 0, 2/3, -1, and then I want to dot it with 3, 6, -3, right? So PQ, and then this becomes PQ dot n. So that's equal to 0 plus 4 minus 3, which is equal to 1. Oh, whoa, no, plus 3. Whoa, whoa, whoa. Okay, so that's equal to 7. Whoops, okay. Okay, and then now the magnitude of n is equal to 9 plus 36 plus 9, which is root 54. Okay, and then that means, well, we want to take the absolute value of this guy, which is still 7. And so that means my distance then is equal to 7 over root 54, which rounds down to being 7 over 3 root 6, I think. Okay, and so that's how you do a distance from two parallel planes. Again, you have two planes. One of them, you just find a point and then treat that point if it's in space. Okay, so like this red point out here. And then you find a point in the other plane, and we use the normal to this plane. Got it? Great. So lastly, we want the distance between, so I use B/W to indicate between a lot, two skew lines. And these are a little harder to calculate, and they're also kind of funky. And they don't show up much. So what is a skew line, right? A skew line is, just think of it, if you hold out two, okay, so if you hold like two pencils in your hand and you form an X, right? You form an X with the pencils, so like they touch each other, like that, so there's the clack sound. And then if you lift one above the other, in three-dimensional space, these lines aren't parallel, but they're never intersecting each other, right? And so let's say then L1 is this line. X is equal to 2t plus, let's see, 2t plus 4. Y is equal to 2t minus 3, and z is equal to t plus 1. Hold on, I'm trying to. This is weird. Okay, no. Let's. Okay, so x is equal to 2t minus 2, y is equal to 2t plus 1, and z is equal to negative t minus 1. Okay, and then L2 is equal to x component, which is, let's say this is negative s plus 1, y is 2s minus 1, and z is 4s plus 2. Okay, and so how do we find the distance between two skew lines? Well, I don't want to go through the theory too much, but essentially what happens is when you got two lines running against each other like this, right, and then you need to find the line that connects the shortest distances, right? The line between if you draw a line from one line to the other, that connects the points on both lines, that's going to be the shortest distance point. It has to be perpendicular to both lines, right? So what does that mean? Well, that means that you got to cross the two vector components. And so step one is to cross the vector components. So cross the vectors. And so for L1, right, we have then this is -2, 1, -1 plus t times 2, 2, -1. Or I copied this down wrong. Let's make this a 3. It's not like make the y guy a 3, not the end of the world. Okay. And then for L2, we have x. We got 1, -1, 2 plus s times -1, 2, 4. Okay, so we got to cross these two guys. And what is that? Well, that is, let's say this is v cross w. Let's call it that. So this is v and this w is equal to ijk 2, 3, -1, -1, 2, 4. All right, and that's going to be equal to 14. That's a 2. -7, and then +7. Okay, and so this is what we have. And then the next part is, so essentially what we found then is at some point, somewhere we found a line. We found the shortest distance. Okay, this is the normal. Now we need to pick a point on each line such that we get something that looks like that, right? So if we pick 2 points on each line and then we connect them, we get, a vector connecting the 2 random points on each line. And so now we need to find that vector. So step 2, that's not, I don't know how that turned into 3. Find a point on each line. And that's easy, right? We can just take -2, 1, 1, -2, 1, -1, and we can take 1, -1, 2, and now we want to connect these guys. So let's call that P and let's call that Q, right? So P is on L1, Q is on L2, and the vector PQ then is equal to 3, -2, 3, okay? So let's say we have P and we have Q, right? And this guy here goes in the direction of N. What do we want to do next? Well, what we want to do next is that we essentially want to project PQ down onto this guy, right? We essentially want to take PQ and we want to find the projection of PQ onto the normal vector. And how do we do that? Well, step 3 is how we find the distance, right? So step 3 essentially is use the scalar component to find D, right? And remember what the scalar component was. Remember the projection of a vector u onto v, which in our case then it's the projection of PQ onto n, right? We're trying to project this red line PQ onto this normal vector n, which is this guy here too, this purple guy here too, because it's perpendicular to both. That's equal to, right? It's equal to PQ dot n, right, over magnitude of n squared times the vector n, right, which was also equal to PQ dot n over the magnitude of n times the unit vector n over n. And so what we want to do then is we only want this part right here. This part right here tells us the distance, because what is the length of n over n over the magnitude of n? Well, this length is equal to 1, and this is a scalar which scales how long that projection is. So once we find the scalar which scales the length of projection, we're done, because that tells us how long the distance between the two lines are. So we only want this part. We only want PQ dot n over n, or the magnitude of n, which is equal to um, PQ, so it's 3, -2, 3, dotted with n, which is 14, -7, 7, right, from above. Okay, right here. That's the normal vector. It's n. Okay, and so and we want the magnitude of n, which is root some garbo PQ dot n over the magnitude of n, with 196 plus 49 plus 49. All right, and so on top you get 42 plus 14 plus 21, which is 77. And on the bottom, you get essentially 49, 49. This has a 49 in it, so it's 7 root 6. And so this is 11 root 6. Okay? And of course, if this dot product was negative, it needs to be positive. So you need to put some absolute value signs on it, because it doesn't make sense to have negative distance. Cool. We're done. So these are the steps that you need to take to find distances when you have parallel planes, parallel lines, and skew lines. And I think there's one more thing I want to cover. I believe from above, scroll up. I think it was just some last problems. Other examples like angles between planes. I think I have one more that I can cover, if I can remember to dig it up. And then we can finally move out of chapter 12, which is actually, I didn't expect it to be this long for such a short chapter.